Any solid object to some extent has an ability to either compress or elongate under the action of a force acting on it. And that ability of the object to either compress or elongate is defined as the elasticity of the object. Moreover, that relationship between the force applied and the amount of elongation or compression is given by Hooke's law to be the following: F equal minus kx. And later on we are going to be tackling the significance behind each parameter. But first off, what is Hooke's law? Hooke's law is a principle of physics that states that the force needed in order to extend or compress an object by a certain distance x is actually proportional to that distance, meaning that the force is proportional to either the amount of elongation or the amount of compression. However, that proportionality that exists between f and x is not always valid, but rather it has its limits. And if you exceed that limit, therefore Hooke's law is no longer going to be applicable because the proportionality between f and x is no longer preserved. Now, a famous example where Hooke's law is applicable is actually a spring. So, if we consider over here that we have a spring that is being suspended from a ceiling. Therefore, the initial equilibrium position of that spring is going to be none other but its natural length as 0. Now, if we bring a mass and we suspend it from that spring, therefore the spring is going to elongate by a certain amount. So now we are suspending a certain mass from the spring, and in that case the spring is going to elongate by a certain amount from its equilibrium position, and therefore, so let's call that amount of elongation to be y. Therefore, the new equilibrium position of the spring would be located at the initial length of the spring plus the amount of elongation y. So over here, that parameter, which is either the elongation or the compression, it depends on the direction in which the elongation is happening. So over here, I have assumed that we have a horizontal compression or elongation, therefore I have taken the variable to be x. Over here we have an elongation along the vertical, therefore I have referred to it as y. Now, if you pull that mass down a little bit and you release it, therefore the spring is going to enter into an oscillatory motion, meaning that the spring is going to undergo compression followed by an elongation, compression followed by an elongation. So we have an oscillatory motion. However, whenever a spring enters into an oscillatory motion, that implies that the spring is actually exerting a force in order to retain its original shape back at L0 plus y. So the spring always tries to go back to its initial equilibrium position at L0 plus y. And that restoring force that the spring is exerting is actually given by Hooke's law as F equal minus kx. So that equation over here, which is given by Hooke's law, is none other but the restoring force which is exerting by the spring in order to retain its original shape. So over here we can refer to that force as a restoring force. So what does the minus sign in that case signify? The minus sign over here, it signifies that the restoring force is always acting in the opposite direction of the displacement. So if the spring is elongating, therefore we have a downward displacement, then for the restoring force would be acting upwardly, trying to bring the spring back at L0 plus y. Now if the spring is compressing, therefore the displacement is an upward manner. In that case, the restoring force will be acting downwardly, trying to bring the spring back at L0 plus y. So the minus sign is simply to indicate that the restoring force is always acting in the opposite direction of the displacement. Now regarding that parameter k over here, what does it signify? K is simply the spring constant or the stiffness of that spring. So k, it's a measurement of resistance. It simply signifies the amount of resistance that a spring would exert in order to retain its original shape. So the bigger k is, therefore, the higher the force is going to be in order to cause a change in the elongation of that spring. And the smaller k is, therefore, the lesser the mass is going to be, or the lesser the force applied is going to be in order to cause a change in the elongation or the compression of that spring. Now in our case today, we are not going to be studying the oscillatory motion of a spring, but rather we are assuming that the spring and mass system are both at equilibrium. So if they are at equilibrium, that implies that the summation of all the forces that are acting upon that system is actually equal to 0. But what are these forces? Over here, first off, we can identify the weight, Fg, which is equal to the mass times g. And then we have over here none other but the restoring force, which is acting in the opposite direction of the weight, trying to bring the spring back always to equilibrium position. So in that case, we have over here Fg minus F restoring equal to 0. So that implies that Fg is equal to F restoring. And that would be in the case of equilibrium. That would be whenever the spring and mass system is at equilibrium. So in that case, we can write down over here that Mg is equal to minus Kx. So as we can see over here, the mass suspended and the elongation, they are directly proportional to each other, which is actually logical because the force and the amount of elongation or compression, they are directly proportional to each other. So whenever we increase the suspended mass over here, the amount of elongation is going to increase. So for example, let's say for a certain mass M1, we have a certain elongation X1, or let's call it Y1 in that case, since we are studying the elongation along the vertical. So for a certain mass M1, we have a certain elongation Y1. For another suspended mass M2, we have another elongation Y2, etc. For another mass M3, another elongation Y3, so on and so forth. So now after finding several measurements for the masses and the corresponding elongations, therefore we can find the force applied and therefore plot the force versus the displacement. And over here we have shown that the weight or the force applied is none other but the restoring force. So in that case, since we have the suspended masses, therefore we can find the force applied, which is going to be none other but mg. So in terms of magnitude, the restoring force is equal to the weight. So in that case, we can start by finding, let's say, F1, which is equal to m1 times g. That would be the first force applied. Then after we change the mass to m2, we have another force applied, F2 equal to m2 times g, then F3 equal to m3 times g, so on, etc., so on and so forth. So after having several values for the force applied, and over here having measurements for the displacement, therefore we can plot the force versus displacement. And like I said before, the relationship between the force and the displacement is actually a linear relationship. So we expect to have a straight line for the relationship that relates the force to displacement. However, we cannot keep on increasing the mass indefinitely. We cannot keep increasing the suspended mass indefinitely and keep expecting to have a linear relationship between the force and the displacement. We are going to reach a certain point where that proportionality between f and x is going to be broken. So we are going to reach a certain limit over here where that relationship is going to be no longer linear. And in that case, Hooke's law is no longer applicable. And that limit over here is going to be called the elastic limit. So that limit that we have over here, we refer to it as the elastic limit. Beyond that limit, Hooke's law is no longer applicable and the spring now is deformed. So Hooke's law is going to be applicable along that linear stretch where we have a linear relationship between the force and the displacement that you are going to be solving. The report consists of two parts. However, the measurements in both parts are actually the same. The only difference that in each part we are using a spring of a different spring constant. So we are checking how varying the stiffness of the spring is going to affect from one side the amount of force applied, and from the other side it's going to affect the elongation. So over here we have values for the suspended masses from the spring, and as we can see the mass is increasing with each trial. And over here we are determining the force, and as we have seen before, the force is going to be none other but the weight of the suspended mass. So over here you have 10 grams, you convert it to kilograms, you multiply it by g, that would be the value of the weight. Then the same thing for the rest of the trials. And over here we have values for the displacement. Now the first question over here, they ask you to use linear regression. You have to apply the linear regression method in order to find the slope of your graph, meaning the slope of force versus displacement. So we are finding the slope of force versus displacement. So the force would be the y variable and d would be the x variable. Using your calculator, you apply linear regression and you find the slope of f versus d. After you find the slope, now we know that the relationship relating the force to the elongation is given by Hooke's law as F equal to Kx. So over here F would be your y variable as it was stated over here, and that x would be none other but the x variable, meaning the amount of elongation will be none other but the x variable. Therefore, whatever term that you have which is multiplied by x would be your slope. So over here the slope is none other but the stiffness of the spring. So after you find the value for slope using linear regression, you equate the value of slope to k and you find the stiffness of the first spring. Then you have to repeat the same thing in the second trial. In the second trial now we are using a spring of a different spring constant. And as we can see over here the mass has changed. So now we are using a stiffer spring. So a stiffer spring is going to require a bigger force in order to cause a change in its displacement, a change in its elongation. So over here the force would be none other but the mass times g everywhere, and you have values for the displacement. Like in the case before, you apply linear regression in order to find the slope of f versus displacement, which is given by Hooke's law to be F equal Kx. Once you find the value for slope, you equate it to k, which is none other but the spring constant, and therefore you can compare your experimental value for spring constant to the theoretical one, which is going to be provided for you. And that would be it for Hooke's law. In today's experiment, Hooke's law, we are going to be studying the case of two springs of two different spring constants, or of two different stiffness. So the experiment is going to be divided into two different parts. However, the measurements in each part, they are actually identical. They are the same. You are going to be suspending masses from two different springs, and you are going to be detecting from one side the amount of elongation, and from the other side you are going to be checking the amount of force which is needed to be applied on that spring in order to cause an appreciable elongation within it. And we are going to check later on that when the stiffness of the spring is large enough, therefore you are going to need a greater force or a bigger amount of masses that are going to be suspended from the bottom of the spring in order to cause an appreciable elongation within that spring. Over here, if you look at the apparatus, we can see that we have, first of all, a force sensor. The force sensor is going to be collecting data which has to do with the suspended masses from the spring, and therefore these data are going to be transferred toward the scientific interface over here, and then the scientific interface is going to be connected to the Hooke's law software on the computer, and therefore it's going to be transferring the data which has to do with the amount of force applied to that spring toward the Hooke's law software. So on the Hooke's law software we are going to be reading the amount of force which is being applied on the spring. In other words, we are reading the weight which is applied on that spring, which is none other but the weight of the suspended mass. In addition, if we look over here, at the bottom of the force sensor we have a suspended spring, and then at the bottom of that suspended spring we are tying a mass hanger. So whatever force that we are going to be applying on that spring, we are going to suspend its masses on top of that mass hanger. In addition, on one side over here we have a ruler, and the role of the ruler would be to detect the amount of stretch that the spring is going to undergo whenever we suspend masses from that mass hanger. So in the first trial, before we suspend any mass on top of that mass hanger, we are going to start at a certain reference value, which is going to be none other but the zero reference value. So we are going to bring a ruler over here and place it horizontally at the bottom of that spring, and we are going to be checking the reference value for that spring before suspending any masses from it. So as we can see, the 500 index mark over here is going to be none other but the 0 index mark. It's going to be the reference mark, or the point at which that spring over here would be at equilibrium position. Then we are going to bring a certain mass. Let's say we are going to start with an amount of 20 grams. So we are going to be suspending 20 grams from that mass hanger over here, and therefore the spring is going to undergo elongation. As we can see, we are going to wait until the spring is at equilibrium, it's no longer oscillating up and down. Then we are going to bring the ruler and we are going to check the amount of elongation. Like I said, the 500 mark over here is going to be the 0 index mark, the 0 reference mark. then we are going to be checking now the new position of the spring after suspending a mass at the bottom. So it's around 460. So we have over here an elongation of almost 4 centimeters. So that mass, which was suspended from the spring, it caused an elongation of 4 centimeters within that spring over here. Now, in order to find the value of the force which is applied to that spring, we can click over here on record and get a certain value, which is 0.22 newtons, or simply we can do the calculations ourselves. Since over here we have a suspended mass of 20 grams, therefore the force applied is going to be none other but the weight of that suspended mass. So you multiply 20 grams by G, but you have to convert 20 grams to kilograms first of all, and then you multiply it by G, and that would be the magnitude of the force which is being applied to that spring over here. Then in the second trial, now you are going to increment the value of that suspended mass over here. So let's say now we are bringing another 20 grams and we are placing it on top of the first 20 grams. So now the spring, it elongated furthermore. So to check the value of the new elongation, we are going to bring the ruler and we are going to place it horizontally. So now we have a stretch of around 8.5 centimeters. So again, the reference mark is always 500 over here. So over here we have an amount of stretch of almost 8.5 centimeters. So the 40 grams over here, it corresponds to a stretch of 8.5 centimeters. In order to find the value of that force which is being applied on that spring, we are going to click on record over here, and we are going to get the new value of the force which is being applied on that spring. Or like I said before, you can find that value simply by applying the equation F equal mg. You have the mass which is 40 grams, you convert it to kilograms, you multiply it by G, and you get the value of the applied force. That would be for the first part. In the second part, we are repeating the same thing all over again, but this time we are replacing that spring with another spring that has a different stiffness, a different spring constant. And like I said before, whenever you use a spring of a different spring constant and whenever that stiffness of the spring is too high in comparison to the previous one, therefore you are going to be needing a much bigger force, a greater mass to be suspended from that spring in order to cause an appreciable elongation within it. And therefore you would be studying the relationship between the amount of force applied and the corresponding amount of elongation that that force can cause within that spring.